Bismillahirrahmanirrahim. Assalamu alaikum students. Today we discuss rotational dynamics. Rotational dynamics is our new chapter. In this chapter we study about the motions of object that moving in a circular path. There are different type of motions. When an object moving in a linear path means object moving in a horizontal path, vertically or horizontally, along x-axis or along y-axis, that motions of object known as linear motions. When object is vibrating about its mean positions, let's suppose this is mean positions of the object, and the object is vertically upward, downwards and vertically means propagating along its mean positions, that motions of object known as vibratory motions. And when object is rotated, that motions is known as rotatory motions. And when object is revolving along in a circular path is known as circular motions. In this chapter we discuss only rotational motions, and our aims to find in this chapter the formula for the kinetic energy, work, power, torque, and the functions of rotational parameter phi, omega, and alpha. And there are two main topics in this chapter: perpendicular axis theorem and parallel axis theorem, and their applications. Different applications: perpendicular axis theorem and parallel axis theorem. So first we discuss what is rotational motions. Our first topic is rotational motion. We define as the motions of a body about its axis of rotations is known as rotational motions. The motions of a body about its axis of rotations. Let's suppose this point is center of a circle, and this point is known as axis of rotations. Let's suppose here a particle at point A. Starting from point A to move another point to reach at another point B. Let's suppose the distance between point A to the center of the circle is R, and point B to the center of the circle is R, also R. Here we can, if the object move in a linear path and its initial path point is A and its final point is B, here we can say that this object cover, when object A moving A to B, this object cover 2 meter, 1 meter, centimeter. But here we cannot say that this object cover 2 meter distance, 3 meter distance, 4 meter or 3 centimeter, millimeter. Here we cannot say that, because here a new term introduced known as theta. What is theta? The motions of a body about its axis of rotations is known as rotational motions, and here this theta is known as angular displacement. The angle subtended by an arc. Arc means point A to B. is arc. This is arc. The angle subtended by arc at the center during angular motion is known as angular displacement. And in this figure, here theta represents the angular displacement. The units of angular displacement, unit rotational motions, and second angular displacement. Now here we discuss units of angular displacement. The units of angular displacement is degree, revolutions, or we can say that radian. In one complete circle there is 360 degree, and if object starting from point A going to B and again reach to point A, object cover a one complete cycle, or we can say that one revolutions. And in one circle, in one revolutions there is 360 degree. In one revolutions there is equal to 360 degree, or one revolution is equal to one revolution is equal to 2 pi radian, is equal to 2 pi radian, or 2 pi radian. Here we comparing these two equations, so that 2 pi radian is equal to 360 degree, so that 1 radian is 1 radian is equal to 53.7 degree. Now here we discuss angular velocity. Now here students, we define angular velocity. We can say that the rate of change of angular displacement is known as angular velocity, or time rate of change of angular displacement is known as angular velocity. The units of angular velocity is, in System International, unit of angular velocity is radian per second, or other units, that is non-SI units, degree per second and revolutions per second is unit of angular velocity. Consider a particle P is moving in a circular path in a counterclockwise directions. The positions is OP. Let's suppose particle start from point P to moving another point P1 and making angle theta 1. Here subtended angle theta 1. The particle start from P to P1 in time t1. And from point P2, or we can say that the particle start from point P to point P to point P2 means here particle reached at point P2, and here the total angular displacement is theta 2. The particle when moving from point P to P2 taking time T2, so that angular velocity can be represented by omega, and the average angular velocity can be represented as average angular velocity. The average angular velocity mathematically we can write as is equal to total angular displacement theta 2 minus theta 1 divided by, or we can say that T2 minus T1. Here theta 2 minus theta 1 is del theta, and T2 minus T1 is del T. These equations represent the average angular accelerations, average angular velocity. When we take the limit on del theta divided by del T, we can write as, when we take limit del T approaches to 0, then average is equal to limit del T approaches to 0 del theta divided by del T. This term is known as instantaneous angular velocity. Instantaneous angular velocity limit del T approaches to 0 del theta divided by del T, or instantaneous angular velocity can be written as d theta over dt. Now angular accelerations. For angular accelerations we can write as, angular accelerations can be defined as the time rate of change of angular velocity is known as angular accelerations, and its unit is radian per second square, degree per second square, and revolutions per second square is unit of angular accelerations. For angular accelerations, here we can say that the angular velocity omega 1 and here omega 2 at time t2 and in time t1, so that average angular accelerations is equal to omega 2 minus omega 1 divided by t2 minus t1, or this can be written as alpha is equal to average angular, so that this represents del omega divided by del t. This equation is known as average angular accelerations. For instantaneous angular accelerations we can write as v taking limit del t approaches to 0, alpha is equal to del t approaches to 0 del omega divided by del t. This term is known as alpha instantaneous is equal to limit del t approaches to 0 del omega divided by del t, or we can instantaneous angular accelerations is equal to d omega over dt. Instantaneous angular accelerations means the accelerations at any instant, or instantaneous angular velocity, the velocity at any instant is known as instantaneous angular accelerations and instantaneous angular velocity. Students, now here we discuss the vector form of angular velocity. Consider a three-dimensional case and suppose that point P is located at a distance r from a center, or located at a distance r from the origin, and that point P is revolving or rotating about z-axis or in xy plane. The angular velocity omega is directions along the z-axis, so that the directions of angular velocity is along z-axis. The linear velocity and angular velocity are related as the linear velocity and angular velocity. Linear velocity v is equal to, can be written as v is equal to omega. Omega is angular velocity into radius vector, the radius of circle. So here we can say that the r sine theta, radius of circle here formed as v is equal to omega into r sine theta. As we know that the torque is equal to r cross f, torque is equal to r f sine theta. When cross product open, we can write as sine theta, so that these equations can be written as v is equal to omega cross r. R in vector form, v is equal to omega cross r. Here v is linear velocity, omega is angular velocity, and r is positions vector. These equations represent the relations between linear velocity and angular velocity. We can say that v is equal to omega cross r is the relations between linear velocity and angular velocity. Now here we discuss the vector form of angular accelerations. Now, for the vector form of angular accelerations, we can write as, consider a three-dimensional case in which a point, taking a point P located at distance r from the origin, so that point P is moving about are rotating about z-axis. The directions of angular accelerations along z-axis, but here two cases. First, we represent the radius of this r sine theta. If the angular accelerations is increasing, so that their directions is, as we know that directions of angular velocity always in vertical upward directions. How we find the directions of angular velocity? For finding the directions of angular velocity, we use right hand rule. The curved finger indicating the directions of a particle and thumb indicate the directions of angular velocity. So here the particle moving in a counterclockwise directions, so that here thumb indicate the angular velocity directions in upward directions along z directions. If the angular accelerations is increasing, so that the directions of angular accelerations is upward, angular acceleration is represented by alpha, and if the angular accelerations is decreasing, then the directions of angular accelerations is downwards. For increasing case, both are parallel, and for decreasing case, both are anti-parallel. Now, the vector form of angular accelerations. From previous result, we know that V is equal to omega cross R. Differentiating these equations, dV divided by dt is equal to d over dt omega cross R. As we know that dV over dt is linear accelerations, A is equal to product rule d omega divided by dt R plus omega cross dr divided by dt. Now A is equal to d omega over dt. d omega over dt is angular accelerations represented by alpha cross r plus omega, and dr over dt is linear velocity. Giving name equations 1. In equations 1, alpha cross r and omega cross v. Alpha cross r, this represent the tangential accelerations, and omega cross v is radial accelerations. So that equations 1, A is equal to alpha cross r is at plus omega cross v ar. Linear accelerations is sum of tangential accelerations and radial accelerations. Students, in next lecture we discuss rotational kinetic energy of a body. When a body moving in a circular path, we find formula for its kinetic energy, and we also discuss the moment of inertia. Then we discuss the parallel axis and perpendicular axis theorem.